Okay, so now let's continue with our class, where today we will look at register, another kind of sequential circuit. All right, so last week we have learned how to create a memory circuit, which is a flip-flop, and flip-flop and latch can be or can store only one bit of information, one bit data. Now, if you want to store more or bigger, a bigger size data, for example, 2-bit, 3-bit, 4-bit, 8-bit, 64-bit, so you need a circuit that we call a register. All right. So a register is simply a flip-flop that we connect together. All right, or we can say that it is a set of n-bit flip-flops that is used to store an n-bit information. So for example, if your information or data is 8-bit, so n is 8, so you need to have n or 8 flip-flops, right, in order to store that data. All right, and a common clock is used for each flip-flop, means that you need to connect all the flip-flop to a common clock or the same clock signal. All right. So for example, if we have a 4-bit system, so to store a 4-bit data or information, so you need to have four flip-flops like this. Okay, and where the clock is connected to all of the flip-flops, right, using the common clock. And we can see that the input here, right, just an input, just like 1-bit flip-flops, where you have input, one input to the flip-flops and one output here, right. So if you have 4-bit, so here we name it as A3, and this one A2, and output to Q2, A1, output to Q1, A0, output to Q0. So now you have a 4-bit register where you can store a 4-bit data. All right, for example, your data is 4-bit, A equal to 4, for example. So you can have something like this. Right, so for example, you have 4-bit data and your data is 0, 1, 0, 0, which is number 4, and the output should be 0, 1, 0, 0. Okay, so the data can be stored in these flip-flops. Now, how to model our register in Verilog? So to do that is straightforward, just like what we did in flip-flops, but now the input and output is not 1-bit anymore, but more, the size is bigger. So in this case, so see module, so this is the name of our module, rec4, and you have clock input, you have A input, you have Q output, and clock is 1-bit, the clock, and you have A is 4-bit now, which is A3 to A0, so A3 to A0, and the output is the rec data type, right, because we assign a value to Q, and Q is inside always block. Okay, so rect data type, and of course Q, the size is 4 bit, Q3 to Q0, 3 to 0 Q, and this is how we model or create a register, always just like what we did in flip-flops, post edge, right? Because the clock is positive edge triggered. So if you have something like a bubble here, means that this one is negative edge. So what you need to have here is negative edge. Okay, but in this case we have positive edge. So the code must be post edge, positive edge, and clock, and Q or A is assigned to Q, right, or E equal to E. And the assignment here, you see, the assignment is used non-blocking assignment. All right, where the symbol of assignment is this instead of this. And the simplified circuit or block diagram is this, yeah, where input now is 4 bit, the output is 4 bit, and you have the clock here. Okay, so quite simple, straightforward. Now look at the other useful register, right, or practical register. So when you draw a register in later on in your circuit, maybe you can have something like this, a box. OneBit register is a box, and you have input and you have output. The output is 4 bit, for example. The input is 4 bit and the output is 4 bit. And normally a register, you have one signal that control whether the input can enter the register or not. So this input is called load. All right, the load input, where if load equal to 0, and the input here A will not go to the register yet. All right, but when load equal to 1, A will go to or go into the register. Okay, so what is the circuit inside, or how to design that kind of register? Okay, so we will use the multiplexer actually for the load signal, right? So in this case, we can see that if load equal to 0, this should be 0, 1, bigger, 0, 1, 2 to 1 multiplexer. Okay, so if load equal to 0, we can see that the input to the register is the previous value of the output, which is the Q. All right, same as the second flip-flop, the third one and the last one. But when the load value is equal to 1, so the input A will go into the register or to the flip-flops. All right, and also in this case, this flip-flop we have a reset signal. All right, and of course this one is positive edge triggered flip-flops or register. Okay, so a register is actually, if you learn in your previous course or in your undergraduate course. So if you learn microprocessor, for example, so you will have many register in your microprocessor, right? So a register is actually temporary memory for your microprocessor. So for example, if you learn ARM microprocessor, you have many general purpose register, right? From R0 to R15. Or if you learn PIC microcontroller, you have general purpose register, and you also have special function register. All right. Or if you learn Motorola microprocessor or Intel microprocessors, you have general purpose register and a special purpose register. So that is the kind of register or the application of the register to store the information or data temporarily. So normally when you want to insert the data into the register, so we need to have a load signal. All right. So whenever the load signal is active, or equal to 1, so the data will go into the register. If load equal to 0 or inactive, so the data inside the register will remain the same. Okay, so that is the idea. So now we will learn how to design this kind of register, especially using the Verilog. How to model this register. So, and again, you are encouraged to build the 4-bit register using hierarchical modular design technique. So you can have one flip-flops, and you can have multiplexer, and try to design this using a hierarchical design. Right? We have learned this in chapter 2, chapter 3, chapter 2, right? Okay, so here is how we write the Verilog code or model the register with load signal and the reset using Verilog. Okay, so let's name our register as rec4, and now we have the clock. All right, 1-bit clock. We have reset, and we have load signal, and we have A, we have Q. All right, so our input, 1-bit input is clock, reset, and the load. And A is 4-bit, so 320, 4-bit, and Q is of course the output, and it is a 4-bit, Q3 to Q0, 320, and we need to declare as rec as well. And to do that, we need to have always block, and of course positive H clock, positive H here. And now we have reset. Reset. So if our reset is positive, means that if this reset signal is 1, all right, if the reset signal changed to from 0 to 1 here, means that we reset the flip-flop. Reset means that the output will be 0. Okay, so if it is active high like this, active when the logic is high, so we need to use post H, post H, reset. Okay, and it is not H sensitive actually. This is not H sensitive like the clock, although in the code it is said to be post H. It is actually a level sensitive, means that whenever the reset input is high, the circuit need to be reset, and this we call it as asynchronous clear. So in Verilog, although reset is post H, it is actually level sensitive, means that whenever the reset signal is 1, so the circuit need to be reset. This is different from the clock, where it is active only at the edge. Alright, the clock, yeah, the clock here, active only at the edge, and in this case it's positive edge. Alright, but for the reset, remember it is asynchronous reset or asynchronous clear, means that it is actually level sensitive. Whenever the signal is 1 or active, so the circuit need to be reset. Alright, so that you need to remember. And now how to write the code. So the code is this: if reset means that if reset equal to 1, so the output must be equal to 0, and if not reset or else, and again when we else here, when the circuit is not reset, so we have two conditions actually. Alright, the output will depend on the load signal now. So if load equal to 1, alright, the output or the value inside the register, the output, means that the value inside the register is equal to the input, or A in this case. Alright, and remember when we describe this memory circuit, if we have if here, no need to have the else statement. Alright, because this is assigned to you automatically by the Verilog compiler. So what the Verilog compiler do is that, for this case, you need to have, it will give you else Q is actually equal to Q. Means that if load equal to 0, or load not active, and this is not reset, the output of Q remain Q. Alright, remain the same. Alright, but if we load a new value, so Q should be equal to A. Right, but no need to have this in Verilog, because the sequential logic, when we design the sequential logic, it is created automatically by the Verilog compiler. Alright, so that should be easy to create a load and reset signal for your register. And this is the simplified block diagram of this, where you have input 4-bit, output 4-bit, and you have positive load signal, and you have positive reset, and you have positive triggered each triggered clock. Alright, so it should be easy. Now, how to create a bigger register? Alright, so maybe we can use this parameter. So remember, in chapter 2, parameter is used to define a number that we want to use many times later on. So in this case, we define n to be 16. Alright, and here when we look at the code, we can see that input, of course, clock, reset, and load is 1 bit, and A now is n minus 1 to 0. So if n is equal to 16, means that this one is actually 15 to 0 A. So the size of A is now 16 bit, right? And if we want to change this design to 32 bit, so because we use this n to represent the size of our register, so we can later on change this to 32, and this automatically will be 31 to 0, and this also will be 31 to 0. Alright, So when we use parameter, you can see we can change the size of our design easily, as compared to the previous one where we need to declare one by one. Yeah, so that is the use of parameter. Okay, so just go back to the design where our n now is equal to 16. So this should be 15 to 0, and the output now is 15 to 0 as well for the Q. And look at the code. So it should be the same with the previous one, except that the size is now 16 bit. All right, so if reset, Q should be equal to 0. If load, yeah, Q should be equal to A. And if load equal to 0, remember Q should be remain Q. All right, so this is easy. So let's go to the next. But before that, any question?
Doctor, can you repeat about the post-age reset?
Okay, repeat about the positive age reset. Yeah. All right. Okay. Now I try to explain the reset and the clock. Okay. All right. Actually, good question. So try to have this. Now let's look at this. So for example, we have the clock. Maybe we have the grid so that you can see easily like that. So I have the clock like this. All right. Now I have the input D. This is clock. And this is D. And let's say our clock is positive H. Yeah. So let's say, for example, our D is like this. And let's, for example, maybe make it bigger. This. And let's say we have reset here. Something like this. Okay. Now let's see what is the output. Q. All right. So when we write in Verilog like this, always, yeah, post H too big, push it clock, and post reset. All right. So the clock, the output is now sensitive to the positive edge of the clock. All right. And the reset will be active high. So the output now, we will look at Q. So Q, because D at first is 0, or let's say we start from 0, and from the here is positive H. The first positive H, the Q, the D, the input now is 0, so the output Q should be still 0 until the next positive H here. All right. So here we check the input D here is equal to 1. So D should be equal to 1. And the reset is too early here, so I change a little bit here. Let's say the reset is here. All right. And the next clocks positive H, still D equal to 1. So D here should be still equal to 1. And the next should be equal to this, D equal to 0. So D should be go to 0. But now look at the reset. Reset now is this. All right. Means that if whenever the reset is activated, so your output must be reset, go to 0 all the time. Whenever the signal is activated, in this case, it is activated here. All right. Until here. Now the reset is not activated already. So we will need to look at D. So D, of course, D equal to 0. So just 0 then. But the reset, yeah, will be level sensitive. Means that whenever the reset is active, okay, here, whenever the reset is active, the signal, the output must be equal to 0. All right, and it is not level sensitive, although in the code we write post H. All right, in Verilog, the reset always need to write post H or next H, but it is not H sensitive. Actually, it is level sensitive. If you write next H reset, means that whenever the reset is 0, the output must be 0. Okay, but for the clock, all right, you need to look at the age of the clock. All right, so I give you another example. Maybe use this one. Change this a little bit. All right. Okay, now the reset. Now the reset is maybe here until here. Okay, now what is the output? So the output will be, now look to check the output. So we will look at the clock and also of course the reset. So in here, yeah, here positive H. So here D and no reset. So should be 0. Yes, 0. So and we go to the next clock H, next positive clock H, this one, and we look at D. So now D equal to 1. And of course the reset is not active yet. So we need to go up here and to the next clock H. Okay, still 1. So it should be here because here there is no reset yet. And the next clock H is here and D is still 1. So it will go until here. We can see that the reset is active already, and it is level sensitive. Means that whenever active, you need to go down, reset until here. Yes, reset, but to go down or up again, you need to look at the clock edge. All right, so in this case here 1, so you need to go to 1 here, and the next one still 1 and no reset, so still 1 here and the next. All right, but here reset, here must be reset until here. The next one, we need to look at the clock when the reset is not active. All right.
Okay, doctor. Thank you.
Okay, welcome. Any other question? Okay, so if there is no question, so let's go back to this. This is 16-bit load, a register with a load signal, and of course you have the reset. Yeah. Now come to the another kind of register circuit, and this is very useful in the system, especially in microprocessor or in computer, where the register that we can do shift. All right, shifting. Okay, so in this case, this circuit can do load. All right, where you can load the value inside the register and you can shift the data. In this case, from the left to the right. Okay, so this is how you shift from the left to the right. Okay, how we do that? Okay, let's look at the circuit. So what we can see here is the structure is almost the same, but the difference is that you can see that the input for this for the multiplexer. So for example, when the signal here, load or shift signal here, is equal to 1, if the signal here equal to 1, means that the input to the register, this register, this register, this register, this register, is from here. All right, because the select input for this multiplexer 1, yeah, 1 means that the input for this is from this part. All right, means that if the signal here is equal to 1, we load the signal, parallel input here, we load the signal into the register. All right, but whenever this signal equal to 0, means that the input to the register is from this 0. All right, so from this, the serial input. So for this register is from this, and for this register is from the output of the first register, and for this register is from the output of the second flip-flop Q2. Right, see, and the last one is this one. So it is a serial input, or the shift. Yeah, the shift. This one will go to this one, this one will go to this one, and this one will go to this one, and this one will go to this one, and of course this one go to the output. So we can see that when we have a circuit like this, our register can be a parallel input and parallel output register, and another time when we set the signal to 0, we can have a shift register where the input is in serial. Alright, where from here we go to the from here we go to this one, and from this one we go to this one, and from this one we go to this one, from this one we go to this one. Alright, so this shift register is very useful in communication, for example. Alright, when you transmit a data in serial. Alright, so and for example, you have to microcontroller. Alright, and this is the register, output register for the first microcontroller. This is the second microcontroller. Alright, and you want to transfer the data from here to here using serial communication. And of course, most of the time we use serial communication to transfer data from one device to another device because serial will lower the cost, will save you cost a lot compared to parallel communication. For example, if your system is 8-bit, if you use parallel communication, you need 8 wire at least. For the serial, you need only 1 wire. Alright, so when, for example, the data is 0, 0, 0, 1, 0, 1, 0, so you want to transfer this bit by bit. Alright, 0 will go first, so 0 will receive to this register 0. Alright, then next you want to transmit the next bit, so you need to shift to the right, so you will have 1, 0, 1, 0, 0, 0, 0, and now in the line 1 will go, and here also you need to shift, so the first 0 will go to the next bit, and the 1 will go to the first bit, and you shift to the next and shift to the next until you receive all the data here. Okay, so that is how you use the shift register in your project or your design. Now, how to model our shift register in Verilog. Okay, so before that, so this is another kind of register or flip-flop, or one flip-flop. This is flip-flop with marks in okay, something like this. Right, when you have marks, right, so this is the code for this actually. FD, and you have 0, 1, and you have input cell, and this is D0, this is D1, and you have Q. Okay, so just this, post H, so the clock is positive H. So if select equal to 0, so the output Q should be equal to Z0, and if select is equal to 1, so the output should be equal to D1. Alright, so that is the case. Or you may use this this code all right, where the multiplexer is modeled using the data flow modeling, all right, can also. So this will create the same circuit as this one. Let's go to the, yes, this one, to model our shift load register. All right, parallel load and shift register. So let's have this one so that we can this one. So I want this. Okay, so hope that you can see this, so that I can try to, okay, go back to this. Okay, so these two code is actually used to model this parallel access shift register. Okay, so let's see how we model this using this code. And look at the first one. This one is using the hierarchical code, all right, where we use these one-bit flip-flops to create this one, and we use hierarchical code just like you did what you did in your assignment. Okay, where you where you create the adder subtractor circuit by using the smaller full adder circuit. All right, this is the same, where you use the smaller module, this one, mux DFF. All right, so stage number 3, so let's call this as stage number 3, and you have W as an input, so in this case is D0, yeah, W. So here we name this as W. All right, and R3 is actually this one, so just we name this as R3. All right, so in this case is D1, yeah, D1 is actually R3, and this is L. L in this case is the select signal, which is this one. All right, so in this case we name it as L, and of course we have clock. This one is clock, and the output is, yeah, Q. In this case is Q3. Okay, so that will be the first stage, and the name is stage 3. So this one we can call it stage 3. And this one is stage 2. So the stage 2, the input now is Q3. Input to the stage 2 is Q3. All right. So of course this one is from Q3. Yeah, Q3, and another input is from R2. So this should be R2, and the same signal here, L, connect to this signal, which is L, and clock. Of course, you have clock, and Q2. This one, Q2, for S2. For S1, this one you have Q2 is the input. Q2 is the input for S1, and another one is R1. So this one should be R1, and you have clock, and you have Q1. The output is Q1 here, Q1, and the last stage S0. The input is Q1 and R0. So this is Q1 and R0, and you have L, So this one is L, and you have clock, and you have Q0, right? So this will give you this, and of course you need this as a sub module, which is this one, these two, these two multiplexer and your flip-flop is described or is modeled using this one. All right, and you have another style of modeling where you use the behavioral modeling. All right, so in this case you can do that also, right, by using this. Okay, the name is shift 4, R, L, W, clock, and Q. It's the same. All right. In this case, the Q is declared as wire, yeah, as wire. In this case, right, because Q is inside the always block. All right. And let's look at this. If L, before that always you have post H, and you don't have reset in this case. So post H clock. If L, all right, if L, so Q is equal to R, or R is assigned to Q. If L, so the R, so here is your R, yeah, R, and you of course you have R3, R2, R1, and R0. So if L active, yeah, L equal to 1 in this case, means that all the R here will go to the register in parallel. All right, but if L equal to 0, what happened? So if L equal to 0, now the input to the register is not from R anymore, but it is from this. All right, where Q0, the input for Q0 is from Q1. So whenever L equal to 0, so what we have is that the input for Q0 is from Q1. So let's see. This is Q0. Yeah. The input for this register is from Q1. Exactly. And Q1 is from Q2. Let's see. Q1 here is from Q2. Q2 is from Q3. Q2 is from Q3. And Q3 is from W. In this case, this is W. Q3 is from W. So you will get the same circuit. All right, whether you use this style of programming or code or this one. And of course, if you use this one, you need to have this one. All right, so up to you. And next, we want to look at this. This another shift register where we use the parameter now. All right, and we use the for loop here. Okay, so in this case, n equal to 16, too big. So let's say we change n to 4. All right, in this example, let's just change this to 4 so that we can look at the example. So in this case, when we look at this, if this n equal to 4, so what we have here is R should be equal to 3 to 0, 3 to 0, and Q also 3 to 0, and the rest should be the same. And we have in K as integer here because we want to use K in the for loop. Alright, so we need to declare K as an integer, and K is not a signal, not a signal in the design. It is a integer data type where we will use in our for loop. So now let's look at this. When L equal to 1, so Q is equal to R. So this is the same like the previous code, where when load active, so the input or the value inside the register should be R. All right, so R is loaded into the register. But if L equal to 0, what happened? This. All right, so in this part, when L equal to 0, so when L equal to 0, we have the for loop. So we need, if we want to see or we want to know what is the circuit that will be synthesized to, we need to unroll the loop. Yeah. So to unroll the loop is easy. So we just replace K with the number here. So we start K with 0. So in this case, so you have Q0. Q0 should be, should be Q. 0 plus 1 should be Q1. So the for loop is here, in this box. Alright, this one is not inside the for loop. Alright, because just like you code in C, the for loop, the one that is in the loop is the one that is after the for loop statement. Alright, but if you have begin and end, something like this, end means that all of these statements are inside the for loop. But if you don't have begin and end, and only one statement in after the for loop, the for, alright, means that the one that is repeated is this one. Alright, only one statement. Okay, so now our K is equal to 0, done, this one. Now we need to increase our K, right, because K is equal to K plus 1. And in Verilog, you cannot use K equal K plus plus, just like in C programming. No, Verilog not accept that. Alright, so you need to write K equal to K plus 1. Alright, and K is still less than what? Less than 3 in this case, right, because n equal to 4. Okay, so now our K is 1 is still less than 3, so we need to go back and do the loop. So now our Q is equal to K now equal to 1, Q equal to 1. What? K1 plus 1 you have 2. So this is Q1, this is Q2. And then you update the K from 1 go to 2. Alright, 1 plus 1 you have K equal to 2. Now, and 2 is still less than 3. So you have Q2, Q, 2 plus 1, you have 3. And you update K. Now K is equal to 2 plus 1. You have K equal to 3. And 3 is not less than 3. 3 is equal to 3. So now we need to exit the loop, right? Exit the for loop, because k is now equal to 3 already, right? And exit. So we go to the next line, which is q. Okay. Q3, right? Because exit the loop, you need to update the key. In this case, is equal to W. Right? So we can see that when we use the for loop, we can create the shift register as well. All right. So this code is actually same as this one. All right. And the good thing about this is that when your circuit is big, for example 16-bit now, all right, if you write that this way, so you need to have many statements here. And if that is 16-bit, what about 32-bit or 64-bit? All right, so you need to have very long code. For this one, you just change this to 64, and here still the same. All right, so that is the use of for loop. Yeah? Whenever we want to write or create a big circuit, all right, and the pattern is repeated, so we can use for loop in our code. In this case, we use in the shift register. Okay, so hope you get the idea. Any question? So if no question, we will go to the next, and hopefully we can finish this chapter 3 by today, and next week maybe we can discuss the tutorial and also go to chapter 4. And next week is week number 7, which is the last week of before we have the midterm break. Okay, so let's look at this. This one is another kind of register that we can produce. Okay, with enable input. Actually, it is the same as the load input. Yeah. So if you name it as enable, so you can have something like this, enable input. All right, it's actually the same. Now look at the application of the register, where you can create the counter from the register. All right. So for example, we have something like this. Yeah, this is an up counter. All right, where you have enable input here. So in this case, when we look at the circuit here, whenever enable is equal to 1 in this case, right? If E equal to 1, so the input for D is actually from the output for this register, go to the adder, and this adder is actually the +1 adder. So another one is input is actually 1. All right, so you +1 to the output and you increase the input. All right, so you can write the code like this. Okay, module, the name is upcount, reset, clock E and C, reset. And now the reset is active low. Yeah, you have bubble here. So the bubble here indicate that the reset is now active low, and the clock is active positive edge trigger. All right. So in the code, you can write like this: always negative edge reset, positive edge clock. All right. And if reset equal to 0 here, or not reset, so C, the output should be equal to 0. Yes, exactly. And if reset equal to 1 or not active in this case, all right, so we need to look at another signal, which is E. All right, so if E equal to 1, so the output of C should be equal to C plus 1. All right, so if E equal to 1, so the output from this should be equal to this. All right, which is C plus 1. All right, but if E equal to 0, E equal to 0, or in this case else, C should be equal to C, the previous C. You see, if E equal to 0, the output for C should be remain the same, which is this line. All right, so C should be equal to C. All right, but in Verilog, no need to write this. Remember, this is created automatically when you create the memory circuit or flip-flops, or in this case register. All right, so that is a up counter. You can have another kind of up counter where you have this load signal, all right, and E signal. So whenever load equal to 1, L equal to 1, so this output here will be equal to C will be equal to R. See, but whenever E equal to 1 and load equal to 0, yeah, this is 1 0. This is 1 0. Okay, so whenever L equal to 0, so the input here will depend on this line. All right, this line. So this line will depend on E. So if E equal to 1, so the output C here must be C plus 1. All right, else the output C must be this, must be C. All right, so this is another kind of counter where you have where this counter can come from any number. So for example, yeah, if you have a register, a counter, so for this one, it will be count from 0. Always count from 0 because you cannot input any number to this register, right? So your counter will be, if you draw the register, a box like this, so it will count from 0, 1, 2, and so on. All right, depend on what is the size of the register. In this case, you have 4. All right, so it will count from 0 to 4-bit. All right, 15. Yes. But in this case, because you have option to input any number to the register, so you can have a register. You can start from 0, where you activate the reset signal, so you can start from 0, or you can input a 0 number into this by activate this L signal equal to 1 and R equal to 0. So 0 will go to this, and it will count from 0 to 1 to 2 until 15. Or you can start the counting from starting from number 9, for example, where you can have 9 here at R and set L equal to 1. so that this 9 will go to this register. All right, 9, and you start the counting. All right, so start from 9, 10 until 15. All right, so this counter can start from any number. Okay, so if you want to create this kind of counter, so this is the way, right? And what if you want to create a down counter? Countdown. All right, so if you want to have a down counter, so instead of adder here, what you need to have is the subtractor. All right, and the code is just change this to this. So, and remember in your Verilog code, when you use this operator, all right, A equal to B plus C, this is not OR, yeah. Remember in Verilog, OR is like this. If you want to have B or C is like this. But when you use the plus sign or plus operator, this means that this is addition operation, and the Verilog will assign you an adder. All right, it will use the internal library. All right, the adder library for you. All right, so this means add, A plus B, sorry, B plus C, and assigned to A, is that the output is A. All right, so in this case, when you use minus operator, means that C minus 1. All right, C subtract 1. Okay, and maybe you want to create another circuit that another kind of circuit or counter that will count from, in this case, 4-bit. So it will count from 0 to 15. In this case, 15 is in binary is 1111. And when it's count to 15 or maximum number, it will give you one signal to tell you that the counter is maximum, so you can have this checker circuit. All right, so in this case, TC, you see, what you can do is you have an AND gate, you check C3 and C2 and C1 and C0. If all are equal to 1, so TC must be equal to 1. So give you 1 here. Means that if the value is maximum, you get this signal. So sometimes this is very important in your counter, right? When you create a counter, you want to check whether the number is maximum or not. All right. So if maximum, it will give you one signal, so that you can have a circuit that will manage that maximum value. For example, if maximum, you want to do what? All right. Or maybe you want to have to check if you have down counter, you want to have this. If all of the signal is equal to 0, all right, so you may have something like this. The NOR gate TC, if all equal to 0, the TC will be equal to 1. So that is for to check for 0 minimum. All right, so that will be the counter. Any question? No question? Good. I believe that there are two possibilities. Yeah, whether you lost all the things or whether you absorb everything. Either one. Which one is you? Okay? But no problem, because that can happen, yeah, because we have 3 hours lecture, which is quite long. It's normal, but the good thing is that now we have the recorded lecture, so that you can always refer back to the lecture. Okay, so if you not understand this part, maybe you can try to read the lecture notes and look at the explanation later on. Okay, but today I wish to finish this. We have another 12 minutes. Let's try to finish the final part of this chapter. Hope you are still with me for another 12 minutes. Are you okay now?
Yes.
Yeah. Good. Okay. So now the last part is the memory circuit. All right. And previously, actually, we create the memory already. The register is actually a memory. Now the memory circuit in here, in this case, is actually a memory, just like your RAM in the computer, array of memory. Right? RAM is actually an array of memory where you have many memory location, and each location has a unique address for us to access, to read, or to write to the memory. All right. How do we do that in Verilog? So the memory is simply something like this. We can have, when you learn microprocessor, you have a memory, right? So the memory can have many location like this. So for example, location number 0, location number 1, location number 2, until location number the last one maybe 1K. All right, if our memory is 1K, the last one should be 1023. Okay, so you have many location, and each location is accessed or referred using the address, and this is the address of the memory. So this is address 0, this is address 1, and so on. Okay, so how you create a memory in Verilog? So this is the way. So where you need, the memory is declared as rack in Verilog, and of course the memory is 2 dimension. You need to declare 2 parameter. The first one is the size of your memory, or the width of your memory. So for example, in this case, how big? 8-bit, for example. So this part we call the width. This. All right. So for example, in this case, the width is 8-bit. So 8 minus 1, so it should be 720. Okay. And the name of your memory, in this case, a memory array name or any name that you want to create, use. And of course, you need to specify this the depth of your memory. In this case, is 1K. All right. So in this example, from 0 to 1023. All right. So 0 to yes, 1023. All right. Depth is in this case is 1K. 1K is 1024 minus 1 is 1023. Okay. So for example, yeah, we want to create this memory. The size is 8-bit, and we have 1K memory. So should be from 0 to 1023. So to declare or to create that memory, this is how: rack 70 7 to 0, and from 0 to 1023. All right, and the name is MEM, memory, mem, or whatever name you want to use. Okay, and the question is how to write or read into memory. All right, so to write into memory is very easy. For example, we want to write to location 21. For example, let's say this one is location number 21. So how to write the data to location 21? So this is how. So your data, so the 8-bit data, for example, 8B10001000. So when you do this 8-bit data will go to the memory location 21. So you will have 10001000 here in your memory, right? If you change this to 30, so it will go to location 30, for example, here. All right, so this will be your address. Yeah, this is how we write into the memory. And how to read the value from the memory. Easy. You have a variable, you declare a variable named data, and for example, you want to read from memory 250. All right, location 250. So the location 250 may be somewhere here. For example, you have this value into in memory 250. Right? When you do this, your data will get 011 0000. Right? So this is how we write, and this is how we read. Okay. And let's look at the last one. And this is the Verilog code to define a memory. And I believe this is the last slide for this chapter. So let's see if we have the code like this. The name is RAM1. All right, we can create a RAM in Verilog. Data in is the data in, data out, DDR address, clock WE is the port where address we have 10-bit address. All right, 9 to 0, 10-bit. Data in is 8-bit, means that our data is 8-bit, and we have two input, clock and WE, or write enable in this case. Output, data out, and rack. This is the memory. All right, the size is 8-bit, and we have 1K location. So the block diagram will be something like this: address 10-bit, data in 8-bit, and we have input, write enable, WE, and we have clock, and we have data out for the read. So assign data out equal to mem DDR. So data out, this signal is this, means that if we have address, yeah, so we can read from the memory to the data out. All right, and the write is inside the always block. So this will be depend on this signal where you need to activate the WE signal. If WE equal to 0, so you write. So WE here should be, yeah, I forgot this one. So should be bubble. Okay, because WE is active when it is 0. so it should be active low. All right. So when you want to write, so you need to activate the WE, and you can write the data into the memory, and you need to specify the address. All right. So this is how you create the memory, and try to go back, and you're at home already, right? Try to do this. To practice, so you can create the memory. Okay, this is your memory. Okay, the memory just now that we learned this one. Wait. This memory. All right. And let's say you have temporary register. You create a register. Create a register. Let's name this as input register, and this as output register, right? Where you can load a number. Of course, you have load L. A, for example, we name this is load A, this one is load B. Okay, where you can load data into this register, which is 8-bit data. Load to this register, and you try to send this data to your memory. All right, whatever address that you want. And you try to read the data from the memory to the output register here. Okay, you can do that in Verilog to practice, or to apply how you have learned in this chapter. Right? Okay, I think that will be for today, and we have finished all the chapter 3, and next week we will go to chapter 4, which is the finite state machine, where we will use what we have learned in chapter 2 and chapter 4, all right, to design what we call a finite state machine, FSM. This is a very useful circuit in digital system. Okay, I think that's for today. Thank you very much.